Hi there, Mr. Sutton here, bringing you the BC Calculus 7-3 Extra Practice Number 3 solutions on transformations of Maclaurin series. For this problem, we want the first three and general term of this Maclaurin series generated by this f of x function. So on this one, the key is recognizing that this is essentially a geometric series. We have something over 1 minus something kind of form. So our initial term is going to be whatever's in the numerator here, this x term. And then the r value, the thing I keep multiplying by, my ratio is going to be whatever we're subtracting from 1. So in this case, that's going to be x cubed. So then I can write this out as x plus whatever x times x cubed is, so x to the 4th. And then we multiply by x cubed again, so that's going to be x to the 7th. And then we just keep doing that. So for a general term, then, we can write x to the, let's see here, we start with a power of 1, and we keep adding 3 to that every time. So we can say x to the 3n plus 1, and that just assumes a starting n value of 0. For this one, we're given that dy over dx equals e to the negative x squared, and y equals 2, and when x is 0. We want to represent y with a power series. So you could try doing this by basically writing the equation of y somehow using differential equation reasoning and then turning it into a power series. But that's going to be tough because then you'd have to be able to take the antiderivative of e to the negative x squared, which, I mean, I don't know what that is. Maybe you do. I don't. So instead of doing it that way, I'm going to write a series for dy over dx. And then I'm going to use antiderivatives and the fundamental theorem to work backwards from that. So let's start with the series for just e to the x. Got to start somewhere. I know the e to the x series. That's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, more generally, x to the n over n factorial. And now if I want e to the negative x squared, I'm basically plugging negative x squared in for all the x's here. So that's going to still be 1 in the beginning, but now we're going to have, instead of x, negative x squared. And then for the rest of these, we got to be a little bit careful with our sign rules. So the sign is going to change depending on whether the original exponent on these x's is even or odd. For the even ones, this negative in here is going to become a positive. For the odd ones, we're going to preserve the sign of that negative. So this next one is going to be positive x to the 4th over 2 factorial. But for this next one, we're taking 3 of those negative x squareds and multiplying them together. So that becomes a negative x to the 6th over 3 factorial. And because the sign is going to change depending on whether the original exponent's even or odd, for the general term here, I'm going to have to do a negative 1 to the n, and then x to the 2n over n factorial. All right, so this is the series for the derivative. Now, if I want to take that to get the original function, I can use the fundamental theorem. Since y equals 2 when x equals 0, that's going to count as an initial value. So we can then say that y equals this initial value of 2 plus the integral from 0 to x, whatever x is, of, well, this derivative here. And I'm going to have to write this with a different variable other than x. So I'm going to write e to the negative t squared dt. So this is pretty good, but it's not quite a power series yet. We're going to have to expand this integral. So I have 2 plus, and now I'm going to basically have the antiderivative of all of this stuff. Now this is technically an integral from 0 to x, so it is basically the antiderivative of all this stuff with x plugged in minus the antiderivative of all this stuff with 0 plugged in. But the antiderivative of all this stuff with 0 plugged in, since everything in here is going to have an x, that's just going to end up being 0 anyway. So in the end, all that's really going to be left is the antiderivative of all this stuff with this x plugged in. So that means this 1 is going to be an x, and we're going to be subtracting, this is going to be 1/3 x cubed using our reverse power rule. And over here, let's see here, this becomes a 5 exponent. Dividing by that, we have x to the 5th over 5 times 2 factorial. And here, this becomes x to the 7th over 7 times 3 factorial. And more generally, we're going to have, let's see here, x to the 2n plus 1, and then this is going to be negative 1 to the n over 2n plus 1. Still have that n factorial down there. A lot of craziness going on. But yeah, this is our series to represent y. On this problem, they want us to find the Taylor polynomial P7, so 7th order Taylor polynomial, for f of x equals sine of x at x equals 0, and then use it to approximate f of pi over 3. So this is basically a Maclaurin polynomial. Now, you could do this the long way by taking a whole bunch of derivatives of sine, but we already know the Maclaurin polynomial for sine of x. That's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then we could keep going, but since this is only a 7th order polynomial that they want us to use on this, I'm just going to go one more term. So this is going to be minus x to the 7th over 7 factorial. All we're going to do at this point to approximate f of pi over 3 is just plug pi over 3 into this P7 of x term, or polynomial that I just wrote here. And I am going to use the calculator for this. So to do this on the calculator a little bit less cumbersomely, I'm basically entering this polynomial into my y equals and y1. I'm almost done. I'm just bringing you in at the tail end of this. So our last term here, we've got minus x to the 7th over 7 factorial. So minus fancy fraction, that's alpha y equals n over d. Let me do x to the 7th up there. And I'm going to do 7 factorial. So that's going to be math. Got to go over to the PRB section and take option 4. And let me quit out of there now. And now I'm just going to do alpha trace y1. And I'm going to open a parentheses and plug in, let's see here, fancy fraction. We've got a pi. We're dividing that by a 3. Close that parentheses if you want. And that comes out to about 0.866. For this, we need to find the Taylor polynomial of order 4 for the function at x equals 0. So basically, Maclaurin polynomial, 4th order, and then use it to approximate the value of this function at 0.2. Well, let's start by getting that polynomial. And to get that, let me first write the series for just e to the x, Maclaurin series for that. That's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and I'll go one more because they want a 4th order Taylor polynomial when all is said and done. So we have an x to the 4th over 4 factorial. Now to get e to the negative 2x as a polynomial, and I'm only going to use the x to the 4th term, up to the x to the 4th term for this. So this is going to be p sub 4 of x. I'm going to just plug negative 2 in for all the x's here. So we have still got a 1, but now x becomes negative 2x. And plugging negative 2x in for x here, negative 2x squared is going to be positive 4x squared. Negative 2x to the 3rd power, well, now that's a negative 8x to the 3rd over 3 factorial. And finally, negative 2x to the 4th, that's positive 16x to the 4th over 4 factorial. At this point, to approximate f of 0.2, I'm simply going to plug it into this p sub 4 that I've defined up here, and I'm going to do all of that on the calculator. To make my life so much easier on the calculator, I'm actually going into my y equals here, and I'm pretty much entering this whole p sub 4 of x as my y1. And I mean, it's kind of annoying to write all of this stuff out in here, but you got to figure you're going to be doing it anyway with 0.2 instead of x if you don't do it this way. So this way, I have it all in here. I can make changes if I need to. Now I can just quit out of here. And to plug in, I'm just going to do alpha trace y1 and do, let's see, parentheses 0.2. Now the nice thing about this is I'm letting my calculator take care of all the plugging in and parentheses and all the rest of it. All I had to do is pretty much just enter this function exactly the way it appears here. So pressing enter now, that comes out to about 0.670. On this problem, they want the 4th order Taylor polynomial approximating cosine of 2x near 0. So basically, Maclaurin series for cosine of 2x, if we were to translate that. Let me start by writing the Maclaurin series for cosine of x, which is one of those that we should have memorized. So that's going to be 1 minus x squared over x, or 2 factorial, yep, plus x to the 4th over 4 factorial. And we could keep going with this, but they said they wanted the 4th order Taylor polynomial, so that basically means out to the 4th power in this situation. So now we need cosine of 2x. This is just cosine of x. To get cosine of 2x, we're essentially going to plug 2x in for all the x's here. So cosine of 2x, we're still going to have 1 in the beginning, because there's really nowhere to plug an x in there. And I'm going to say that this is approximately equal to now, because I'm just writing a polynomial. I don't have the dot 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 anymore. If I'm truncating, then I don't have the real value anymore. And now after that, we've got, let's see here, we've got a 2x plugged in for the x in the x squared. So that's going to be 4x squared over 2 factorial that we're subtracting. And if I have 2x quantity to the 4th, that's going to be 16x to the 4th over 4 factorial. And again, no dot dot dot, because this is just a 4th order polynomial, not a series. If you wanted to, you could simplify this. So let's see here. We've got 4 over 2, which is 2. So we have a 2x squared. And if you wanted to simplify this one over here, this is 16 over 24, which we could reduce to 2/3 x to the 4th. So 1 minus 2x squared plus 2/3 x to the 4th. Didn't need to simplify, but there it is. For this free response problem, we have a Maclaurin series given as 1 plus x over 2 factorial and a whole bunch of other stuff for f of x. Our first task is to find f prime of 0 and the 10th derivative of 0 based off of this. So in general, the coefficient for x in a Maclaurin series is going to be f prime of 0 over 1 factorial. That's just the general first power coefficient, linear coefficient. Now, in this particular Maclaurin, we have 1 over 2 factorial as the coefficient of x. So just multiplying both sides by 1 factorial, that means that f prime of 0 must just be 1/2. Kind of using the same reasoning, in general, the x to the 10th coefficient in the Maclaurin series is going to be the 10th power of 0 over 10 factorial. Now, in this particular series, they didn't give us that term, but they gave us the general term, which is just as good. So 10th power term is just going to be, we're going to have x to the 10th over 10 plus 1 factorial. So basically, 1 over 11 factorial is going to be the coefficient in this polynomial. Multiplying both sides by 10 factorial to isolate this 10th derivative, we have 10th factorial over 11th factorial. So this is basically 10 times 9 and all those numbers over 11 times 10 and all the rest of them. So basically, we have 10 times 9 times 8, yada yada, all canceling out, leaving us with a 1 in the numerator and an 11 in the denominator. So then 10th derivative of 0 is just going to be 1 over 11. For this part of the problem, they're saying g of x is equal to x times f of x. They want the Maclaurin series for g of x, first 3 non-zero terms and the general term. So for g of x equals x times f of x, the good news is they already gave us a Maclaurin series for f of x. So to find the Maclaurin series for g of x, we just have to take this f of x and literally just multiply all the terms by x. So that first term of 1 is now going to be 1 times x, or just simply x. After that, we have x squared over 2 factorial plus x cubed over 3 factorial. And they only wanted the first 3 non-zero terms plus the general term, so let's just skip ahead here. This is going to be x to the n plus 1 over n plus 1 factorial. For this last part of the problem, they want us to write g of x, which here it is again. We found this in part B, in terms of a familiar function without using a series. So this is one where you have to kind of think back on the series that you already know. And this is pretty similar to one that we know. There's a series that has 1 plus x squared over 2 factorial plus x cubed over 3 factorial. You know the series it is. It's the very first one you're supposed to memorize. It's e to the x. This is essentially just the e to the x series without the plus 1 or the 1 plus in the beginning. In fact, we could say that e to the x is just going to be 1 plus this g of x series. Well, that being the case, that means that g of x is really just e to the x minus 1. So there's g of x without a series.